Hi there. In the last videos I showed some new modern digital multimeters, but maybe you are more into analog dials and meters that have proven to last practically forever. Here is such a thing, the AVO 8, a truly iconic meter. The AVO 8 was produced for 57 years from 1951 to 2008. This here is a Mark III model. The history of this family of multimeters is amazing. The name comes from what it does. Amps, volts and ohms. From a prototype in 1923 to 2008 it had this kind of unique look. The 1930s meter was really more for electrical work. The AVO 7 was targeted at radio engineers and offered a bit more sensitivity, but by the late 40s the more advanced electronics of TV sets needed yet another boost of sensitivity, which was the AVO 8. Over the next 57 years, the AVO 8 went through a few design changes and, believe it or not, there was even a braille version of the Mark III where visually impaired users could feel where the needle points to. Although there was still a demand for new AVO meters in 2008, the components had become too hard to source and increasingly expensive. A new AVO 8 in that time cost an eye-watering £925 plus VAT or $1,200. There are many collectors and fans out there, and I'm sure my summary is just scratching the surface. I encourage everyone to look at Wikipedia or Google AVO meters, especially Richard's radio site, for more details on this fascinating story. Maybe before diving further in, I should explain how to use an AVO 8 Mark III. I took this picture sometime during the making of the video, and at that time I experimented with restoring some of the writing on the front plate, but frankly I'd rather do something else, and so the meter will probably stay like that. Anyway, normally the connection to the meter uses the two binding posts on the bottom corners. Red is positive and black negative. These are used for everything, amps, volts or ohms. The two binding posts on the top are used instead of the red one to measure DC and AC high voltage up to 2500 volts. To measure DC, you put the right knob, called AC and ohm range, to the topmost position marked DC. Then you can use the knob on the left, called DC ranges, to select suitable DC volt ranges and DC microamps, milliamps and amp ranges. For AC or ohms, the roles of the two knobs are reversed. Put the left one on the topmost position called AC, and now the right knob can be used to select AC voltage ranges, AC current and ohms. Because the AC switch has to select between volts, amps and ohms, the amp range has been reduced to have 100 milliamp as the lowest value to make space for ohms. Speaking of ohms, there are three ranges that use internal batteries, and each one has its own pot to zero the pointer before measurements. To measure resistance, the left knob has to point down to resistance, and the right can be between ohms divided by 100, ohms and ohms times 100. Then there is the ins setting, which stands for insulation, which means it can measure high ohm values in the order of 200 megohms. For that one needs to connect the meter to a high voltage DC of about 130 to 160 volts. And lastly, the mysterious LR setting, which needs an extension unit to measure very low resistance. The button between the knobs right below the logo reverses the polarity of the red and black inputs as long as you hold it down. The button at the bottom center is the overload protection. If the meter is overloaded, it pops out to protect the meter. When the problem is fixed, pressing the button back in resets the overload protection. And that's it. You are now fully qualified to drive an AVO 8. I've got original AVO leads. They are the same super size as the meter itself compared to the leads you have today. Just compare the thickness of the red leads here. I've got mine from eBay with no guarantee that it was still working properly. That's the trouble with these old meters. Anyway, when I applied 6 volt DC, the meter struggled a bit, but that turned out to be the contacts in the rotary switches that had not been moved for ages. With a bit of switch movement, I got the DC volts to work just fine and pretty accurate. The same problem in the AC volts. That's the 10 volt range, but the value is too low. Just wiggling the switch makes it go almost to the right value. Same with 9 volts when the meter shows a little below 9 volts. Here are 26 volts in the 25 volt range and the needle slowly creeps up, but it's still a bit below 25 volts. Then it creeps slowly further to 25 volts and then suddenly it goes to about what I would expect to see. This also turned out to be just switch contacts issue and they are resolved now. Here I run about 100 milliamps DC current through the meter set to the 1 amp range and the value is just at the 10 of the 0 to 100 scale, which is right. Switching to 100 milliamp should get full scale, and it does, actually slightly beyond, which is correct as the current is indeed a bit higher than 100 milliamps. Here's half an amp and the meter is nicely half scale in the 1 amp range. The DC current seems to work better, which could well be because I have used the DC range switch quite a lot when testing the DC voltages before. But the AC current has definitely the worst problem of all ranges. At about 90 milliamps of current and playing with a switch, it is just hit and miss. To cut a long story short, cleaning the contacts fixed the 1, 2.5 and 10 amp ranges, but the 100 milliamps still needs just a little wiggle. Normally that would not be a problem for me since 100 milliamps as the lowest AC current range is anyway not very sensitive, but there is a case where I wish it would work a bit more reliable. And that is with these add-ons. These are 2 of the 4 ranges of current transformers that were available for the AVO series of meters. The left one is the biggest for 400 amps and the other one the smallest, rated 50 amps. The More Pilot 17B, which itself is a large meter, sits there as a size reference. Like the AVO itself, these transformers and their solid metal construction are also very heavy. Normally the AVO 8 tops at 10 amps. To measure more you need either a shunt resistor or, like here, a current transformer. I have connected a soldering iron to the transformer and the other end with the blue leads go to the AVO, which needs to be, you guessed it, in the AC 100 milliamp range. That is possible on mine, but with a lot of wiggling, and as you see the switch is a bit above the 100 milliamps. The problem is you need a known test current to make sure that you got it. But in this case I had it working and so on with a test. Turning the soldering iron on and the AVO reads about 18 milliamps. Since 100 milliamps means 400 amps, we need to multiply 18 by 4 and get 72 amps. That is correct as I confirmed with a clamp meter in the same setup. Luckily I can use those AVO transformers with non-AVO meters just as well, as you see here. 18 milliamps, same value as before. After this brief detour, let's continue exploring this AVO 8 by trying ohms, and upon selecting the range and shortening the leads, I found to my surprise that the needle deflects. So there still was a battery in the meter and it still had enough juice for full deflection or 0 ohms. Adjusting the knob to get the needle exact 0 ohms. Okay, 200 ohms, and yes, the meter is showing slightly more than 200 on the ohm scale. That may well be, as this is a power resistor and not terribly accurate. Let's try 1K, and yes, it shows about 1K, so that seems to work just fine. Trying the ohms divide 100 range for lower resistors, but the needle does not deflect at all when shortening the leads. How about the ohms times 100 range? When shortening the leads, I can get at least half a deflection, but I can't make it full scale using the pot. So half that. Time to check the batteries, because if they have been there left for ages, they may have leaked and caused all kinds of damage. The AVO 8 has a compartment on the top with a cover plate that can be slid off after loosening 2 screws. By the way, batteries in meters like the AVO 8 Mark III are only used for ohms. If you don't want to measure ohms, just leave them out. Well, we have a large D cell that looks to be in reasonable shape and a strange blue squarish battery that I have never come across before. Also just visible are 2 fuses. Getting the D cell out of its compartment takes some effort as the springs hold it tight. Finally it's out. It has a date code of 0999. I take that to be September 1999, more than 24 years ago, but no leaks. These days leaks are much more common than they used to be, probably some cost cutting in battery manufacturing. Now to that weird one which has some discoloration which might be a leak. Finally it's out. It turns out to be an ever-ready type B121. It hasn't leaked yet, at least nothing came out, and messed up the compartment. The label reveals that it should have 15 volts. Let's see what it still produces. About 3 volts. And dropping fast, even when measured with a meter with 10 meg input resistance. It turns out these batteries are extremely rare and expensive, but there are workarounds like a stack of 10 button cells which you can make fit. What about the much more common D cell then? 1.5 volts? Not bad, but that's with no load. Using a battery tester, this loads the battery quite a bit while testing, and the old D cell passes just fine. So why did the divide by 100 ohm show no needle deflection at all? Time to do some more testing, starting with a times 100 range and replacing the 15 volts battery with bench power. With that I can zero the range with no problems. And the 100k resistor shows 1000, but now we need to multiply all values by 100, so 100k. 200k, 300k, 400k, 500k, and so on. 1 meg showing as 10,000 times 100. 2 meg, higher than that, can't be done with a 15 volt battery, and one has to use the ins setting with external 150 volts. Like so. The DC to DC converter, which is one of my other videos, produced the required high voltage. First job is to null the meter by shortening the leads. Doing resistance measurements with 150 volts on the wire is, let's say, interesting, and you do not want to touch anything. Now with 10 megs in series and the needle is at 10 thousandths, but for ins one has to multiply it by 1000, so it's 10 megs as it should. 20 meg, 30 meg, 40 megs, 50, so ins works fine. So why did the divide by 100 range not work? I use the same method and connect the bench power supply set to 1.5 volt to the contacts in place where the D cell goes. The bench power is set to current limit at 50 milliamps, and shortening the leads definitely exceeds 50 milliamps. I guess this was also a contact problem because the needle now definitely deflects. This mode draws a lot of current from a poor D cell. I need to set the power supply to at least 62 milliamps to not go into current limit. But even now I can't zero the meter, and my suspicion is that my test leads just have too high resistance. And sure enough, using a thick solid copper wire between the terminals brings the needle to full range and beyond, and I need to up the current limit to 76 milliamps. I probably should have used the original AVO leads, but anyway, 2 leads made from 1.5 mm core diameter mains wires work just as well. 1 ohm, 2 ohms, 3 ohms, and so on to 10 ohms with a needle at 1000, but since it's divided by 100, that means 10. So it's working fine now, very nice. I tested those extra high voltage terminals for DC and AC and they work fine, as here with a high voltage AC that I increase slowly to 2.5 kilovolts, which is the maximum the AVO 8 can measure by itself without external high voltage probes. Before opening it up, here's one more interesting test. I'm measuring an AC voltage of 100 Hz from my function generator. The blue meter shows the frequency. Watch what happens when I sweep the frequency up to 10 MHz. Not much. The AVO is actually rated to remain at its 2% accuracy up to 15 kHz, but it can exceed that easily. It's a small drop at 200 kHz, but it recovers at 1 MHz, although that's obviously some resonance effect, getting more pronounced towards 10 MHz. Anyway, it seems 100 kHz is definitely workable. So is the AVO 8 the ultimate audio frequency voltmeter? Sadly no. Here I'm feeding 9.2 volts AC and the meter draws 920 microamps from the source. That translates to just 10 kilo ohm input resistance or 1k per volt. Most audio sources except for maybe speaker outputs won't sustain that kind of load. 7 machine screws all around the housing hold the meter together, which then allows lifting off the back shell, which has a short instruction on how to use the meter. And here you have it, all hand wired. My model, the Mark III, was the last where AVO did this. With the Mark IV they switched to a PCB. A quick look into the back shell, which is quite interesting. The connection to the 2 batteries for the ohms is done via the 4 short metal tabs. The longer ones in the far corners connect to the AC and DC high voltage terminals and lead to appropriately sized resistors, which in turn connect to the meter with 2 more of those springy metal tabs. These tabs connect to those metal posts that you see sticking out. This thing is so crammed full of components, which really shows the long heritage in optimizing the placement of everything. Of note, the transformer on the lower left, which handles the AC ranges. Its core looks rather special, probably to support higher frequencies. On the right we have some impressive low ohm resistors for the high current ranges. A view from the underside and the top part with the meter. Those round things you see there are the pots for the ohms adjustment. There are a lot of contacts in this meter. Not only the 2 round range switches with all their contacts buried all the way down there, which you may just be able to spot here and there, but each of these also have some elaborate cam arrangement that moves along under further contacts you see here and there and activates or deactivates them through plungers in a complex pattern as you turn the knobs. Somewhere below in this hard to penetrate mechanical and electrical design is the overload mechanism. That one is mechanically activated through the needle when it crashes with enough force into the limits at the end of the scale, and through a complex mechanism of bell cranks and levers activates the overload switch that sits down there cocked at a hair's trigger. Nowhere did I find data how much overload is needed to trigger the protection. Here I'm putting 10 volts DC into the meter, which gives a full scale deflection at the 10 volt range. Now using the same 10 volts but with the meter at 2.5 volt range. It's a 4 times overload, but the fabled protection doesn't trigger. I don't know if that was enough to trigger it. I don't dare to go higher. The protection might be stuck, so I could really damage the meter. Well, it looks as if this excursion did no harm, but trying to service all these complex mechanics looks very daunting with no guarantee of success, so I rather not mess with it and try to be careful instead. At least the reverse button works, as here, where there is a negative voltage, but when you press reverse, it shows it correctly, as long as you keep the button pressed. If you thought the actual insides of the AVO 8 looked confusing, let me tell you, it's pretty much the same with the schematic. I try to get through it, and at least I understand how the DC volts and amps work, but I admit the AC parts is still a mystery to me, starting with what looks like a full bridge rectifier, but 2 of its diodes are resistors. I tested that on my breadboard and it actually works, sort of, but I don't quite understand why it was done. Maybe diodes were more expensive in those days? Anyway, let's forget the left side and concentrate on the DC, which is interesting enough. So the lowest current range is 50 microamps. I colored the schematic to show the path from the red terminal through the range selector and then up there. This, by the way, is just a contact, not a diode, to the meter and back down through more contacts, including the famous cutout, to the black terminal. It was still not clear to me how that path ended up with a meter showing 50 microamps. So I drew it differently with just the components that do something. It is known that the meter itself is actually showing full scale at 37.5 microamps. The analysis made it difficult because there's a thermistor TH1 in the path to the meter. It is therefore compensating effects of using the meter at different temperatures. I could not find a datasheet, which means I can't determine exactly what resistance is directly in front of the meter. I could measure it, but there's another way. Because the meter is actually a 37.5 microamp type, the second branch formed by the range resistors must eat the extra 12.5 microamps to make the whole circuit consume 50 microamps at full scale. The resistors add up to exactly 10,000, which means with 12.5 microamps flowing through, the total voltage across COM and DC-AC terminals is 0.125 volts. Of course, the same voltage is across the path through the meter, which means we can now calculate that the total value of the combination of resistors and thermistor must add up to 3333 ohms, even without knowing the individual resistor or thermistor values. Now let's look what happens when you select the 100 milliamp range. It's pretty much the same as before, except where the red path was previously coming in at the very left of this string of resistors, it now enters somewhere in the middle. And that looks like this in my simplified drawing. The left part of the string is now directly across the terminals. The values add up to exactly 5 ohms. From the 100 milliamps that go in, all but 37.5 microamps go through these 5 ohms. That accounts to 99.9625 milliamps and results in a voltage drop of 0.4999 volts. The 37.5 microamps flow as before through the meter, resulting in the 0.125 volts that we already know from before. The same current of 37.5 microamps also flows through the right chain of resistors, which adds to 9995 ohms. That results in 0.3748 volts dropping over these resistors. Now, since the 0.125 volt drop across the meter and 0.3748 volts over the right chain are in series, their voltages add up and produce the same 0.4999 volts. It all works out. Lastly, let's consider what happens if we measure 10 volts. Now the red path goes through resistors that are beyond the ones we looked before, which I mark in yellow because they are still in circuit. This is actually quite simple. The top part is exactly the 50 microamp case which we already examined, and we know that this will cause a voltage drop of 0.125 volts. To measure 10 volts, all the meter needs to do is to drop an additional 10 volts minus 0.125 volts or 9.875 volts. It is doing that by adding 2 resistors in series which add to 197.5K. With a 50 microamps current flowing through this circuit, this produces exactly the needed 9.875 volts drop. Although the meter used is actually a 37.5 microamp type, AVO chose to reduce it to 50 microamps to allow for temperature compensation and calibration. A meter that uses 50 microamps has a sensitivity of 20 kilo ohms per volt. The ohm per volt was a measure that was used a lot during the days of analog meters. The higher the value, the better the meter. The 20k per volt of the AVO 8 are pretty much the standard value of reasonable analog meters. There are some with more, but they tend to be more fragile, and anything like 50k or more usually needs electronics, be it transistors or valves, to amplify the input. An example is this post office meter. Some time ago I made a video about it, which also explains the kilo ohm per volt in more detail. This meter states 20 kilo ohms per volt on the front, but as I discovered, it's actually only a 2.2 kilo ohm per volt inside, and the 20k is achieved using an electronic amplifier. They did this because the 450 microamp meter in there is much more robust than a 50 microamp meter, and robustness was the primary design goal, accepting that this meter needs batteries to work, while the AVO 8 does not, except for the ohms. Robustness was also a design of the AVO, which becomes obvious if you compare it with the Selectest Super 50. This one and the AVO 8 are nearly identical in size, function, schematics and the way of operating. The AVO has more resistance ranges, but that's it. Both have 20 kilo ohm per volt sensitivity on DC. On AC, the Selectest is slightly more sensitive than the AVO 8, but even that's still more suited for electrical than electronics work. To be honest, I think the Selectest is far more easy to read, but if you're out and about, I think the AVO 8, built like a tank, is more likely to survive. Should you own an AVO 8 or a Selectest for that matter? If you are a fan of an analog meter, probably yes. Or maybe they appeal for nostalgic reasons, considering the amazing history or the beauty of construction. As a daily meter for electronics, I would not consider either one. For today's electronics, they are just not sensitive enough, and their high load on the measured circuit causes all kinds of undesired effects. If you like my videos, don't forget to subscribe. There are many more projects, repairs and reviews coming up, and it would be great if you decided supporting this channel by becoming a Patreon. Thanks for watching.